Nuclear reactions actually involve breaking scientific laws. Now, laws are not proven. They're just statements of observations that we have observed over and over and over again. Every time we go to measure them, we always measure the same thing. Well, in chemical reactions, we always measured that the amount of mass didn't change, the amount of energy didn't change, just the types, right? So we might burn coal and get carbon dioxide and water out of it, but the amount of mass didn't change, just the type of matter. And we went from having chemical potential energy to having thermal energy. The type of energy changed, but not the amount of energy. And so that led us to establish two laws. The law of conservation of mass, which tells us matter or atoms can't be created or destroyed, and the law of conservation of energy, which tells us we can't actually create or destroy energy. All we can do is change what form it's in. However, when we started messing around with nuclear things, we actually found that the amount of mass can, in fact, change, and the amount of energy can change. So we had to revise these laws. So mass decreases during nuclear reactions, and the amount of energy actually increases. And Einstein's actually the guy who explains what's going on. Einstein wrote down the famous equation E equals mc squared. It's part of his theory of general relativity. And in that equation, E is for energy, m is for mass, and c is for the speed of light. Now, the speed of light is 300 million meters per second. And so that's a really big number, and then we're going to square it. So even a small amount of mass can be converted into a very large amount of energy, which is why the nucleus contains a whole bunch more energy than the energy stored in chemical bonds. Because chemical bonds, we're not changing one thing, and we're not changing mass and energy. We're just moving around the type of energy. This equation just tells us that mass and energy are actually the same thing. They're just in different forms. So much like thermal energy and chemical potential energy are different forms of energy, mass and energy are different forms. That's kind of a weird concept because they're very different in terms of how they behave and act, but that is how we think about it. And so Einstein was able to explain why there's large amounts of energy in nuclear reactions and where that energy is coming from and where the mass went. So the new laws are actually stated a little bit differently. All we did was revise what was there, and it basically says in chemical reactions, energy is conserved, and in nuclear reactions, chemical or energy and mass together is conserved. So the sum of the mass and the energy stays the same, but the individual pieces of mass and energy don't have to. So let's get a quick contrast of the two types of reactions. In a chemical reaction, we have bonds break and reform. And in a nuclear reaction, the nucleus changes. Okay? Part of the atom, valence electrons for chemical reactions. Part of the atom for nuclear reactions, shockingly enough, the nucleus. Do atoms change identities? Absolutely not in a chemical reaction, because only electrons are involved, and electrons don't determine the identities. Absolutely yes in nuclear reactions, because protons are involved, and protons determine the identity. Type of energy, chemical potential energy here, nuclear energy over here. Now don't get in your head that these two energies are somehow unique and different, and nuclear energy can't be used for what chemical potential energy can be. All energy is energy. This is just where it's stored. Chemical potential energy stored in bonds, nuclear energy stored in the nucleus. Amount of energy, fairly small. I mean, dynamite and diesel fuel and gasoline all have lots of energy stored in them, but a nuclear bomb has a whole bunch more, right? So a smaller amount of matter can contain a whole bunch more energy when it's nuclear in energy we're talking about. And is mass conserved in chemical reactions? Yes. Yes, it is. Is it in nuclear reactions? Nope.